Yeah, now that we are familiar with the CIFAR 10 dataset, let's actually go ahead and implement our own residual neural network and train it on this dataset. So for this ResNet from scratch implementation, we are going to use the same CIFAR 10 data module that we just introduced in the previous video. So here are our familiar imports and the preparation of the dataset. And just to familiarize ourselves again how the CIFAR 10 dataset looks like, our Torch Vision utils make grid function, which is also useful for making sure the dataset loads correctly. So let's now take a look at the from scratch implementation. It's relatively, I would say, complicated. So if that doesn't make all sense to you, don't worry about it. And also you may have to actually look at that, let's say line by line without the video, just the code if you want to follow it. I can just tell you though, it's not super important to understand this from scratch implementation, because in the next video, I will show you an easier way of using a residual network. So this is really, I would say, more complicated than it needs to be. But yeah, if you're curious, so this is based on a convolutional 3x3 function that I redefined here. So it's essentially something that we are going to use in different parts. And this whole implementation, by the way, is inspired by a Torch Vision implementation. So I didn't write all of this from scratch. I adopted and changed things here and there. So it's not all even my own code. Anyways, so here we have this basic block class. So in this basic block class, we are defining a block that we are going to reuse. So this is essentially like a residual block. So basic residual block or convolutional block. So what we have is we have convolutional layers followed by batch norm layers, followed by the nonlinear activation function, which is basically what we discussed already when we implemented our own convolutional network 2 videos ago. We have the same thing here again, and then also a downsampling parameter here where we can downsample things if we need to. So here in the forward pass, we are using these. So we are using these different layers we implemented up here. So again, the convolution followed by the batch norm, followed by the ReLU. By the way, we could have actually used also the sequential here to save us some work here. But yeah, this is how it is right now. And notice that we are saving the X here in the beginning. So we are saving that as our residual. So we are later then adding it back, and this creates the residual connection. I would say from this whole implementation, this is maybe the key part where we save the initial value and then apply it later here where we create this shortcut connection. Really, this is, I think, the heart or the essence of the residual network. So let me post this gigantic class here. So this is the PyTorch ResNet 18 class. And then down here, we are calling this make PyTorch ResNet 18 function to create a class PyTorch ResNet 18. So this is again inspired by Torch Vision, which implements many different ResNet versions. And so it is essentially in a way reusable that we can reuse that for different types of ResNets. However, it's maybe unnecessarily complicated here. Again, in the next video, we will see an easier way of using ResNet. This is just to show you really that it's maybe not fun to implement large convolutional networks ourselves, because it's a huge undertaking. This is essentially a research project here where researchers spend a lot of time implementing and coming up with this architecture. And in practice, we want to sometimes or often use existing architectures. So, but to continue with the code here. So this is instantiating this PyTorch ResNet 18. So we are using this basic block that we just discussed above with a certain number of layers here. So let's take a look at our class here. So the PyTorch ResNet 18 class, which accepts this basic block that we just discussed. And then also the layers. So up here, we have the make layers, which are using these blocks. So based on these blocks, we are creating multiple layers. We have, in this case, 4 layers, but of course we will have 18 layers in total because the blocks also consist of layers essentially. So this whole thing is relatively complicated. However, the gist here is that we have the convolutional parts where each block has this residual block where we have the residual connection up here. And then we have afterwards an adaptive average pooling. So we are pooling together the outputs here, and then we are passing that to a fully connected layer. So this is really the classification layer here down down here. And this one, this is really, I would say, almost something you can ignore. This is essentially just rescaling the weight parameters, and that is just to match whatever the researchers implemented in the original paper. So this is really something custom to mimic the data initialization that was used in the research paper. But of course, it doesn't mean that it's required. It's really just to match the results exactly. Okay, so this is in a nutshell how ResNet works. I realize it is probably pretty complicated looking at this. So if you are interested, maybe stepping through this more slowly, line by line would make sense. But the bottom line is really that I wanted to show you that architecture, CNN architecture, is actually a pretty involved undertaking. So it's nothing really, I would say, that we do routinely. It's really takes a lot of time to find something that works well, and then of course also coding it up. So then of course, let's say we have this architecture, we would then continue with our trainer. So again, we can use our Lightning model. It's exactly the same model that we used before. And then we wrap this PyTorch model, where in this case, the PyTorch model would be our ResNet. So here we have this ResNet, which we make our PyTorch model, and then we train for 50 epochs. So larger networks usually train longer, or they require more data and more training time. So this will take a bit. So we will have the fit method, and we will run this now, and it might take a while until it finishes. I should also note that we are using a GPU here. Let's say we are using one GPU. So this is really something I would say that can't run on a CPU anymore, because residual networks are usually really large. So this would take a while. Down here the training starts. And it should take about, I would say, 35 minutes. So it might take a while. So I'm not gonna sit here. I will essentially pause this video, and then I will show you the results, so you don't have to wait 35 minutes until everything is finished here. As we can see, actually 50 epochs was maybe a little bit too much. We didn't need that much, but we can see that the network converges approximately after 10 epochs. And the validation set also converges after, I would say, 20 epochs. So 20 epochs would have been probably the right cutoff. 50 was maybe a bit much. In any case, the network trains quite well. It's overfitting by a lot, so we could technically maybe add some techniques, for example, using dropout or more dropout, and then also, for instance, using weight decay, which I was introducing as an exercise in Unit 6. So there are certain techniques to reduce overfitting. Another one could be data augmentation, which is a topic that we are going to cover also in this lecture. So there are many different techniques. The bottom line is, this network trains, and it reaches about, I would say, 76, 77% accuracy on the validation set, and 75% accuracy on the test set. So this was a notebook essentially showing you how complicated convolutional networks are if we want to implement them from scratch. In the next video, of course, I will show you how we can do this more easily. So in this video, we learned how to implement our own residual neural network and train it on the CIFAR 10 dataset. As you have seen, the neural network code is actually pretty complicated, and since the residual network is such a common architecture, why don't we use an existing implementation of that? We will be actually doing that in the next video by loading a predefined ResNet from the Torch Hub.